Alrighty, hello everybody. Welcome to my Black Hole Lab number 3 by Colin. The introduction of my lab. So part 1 is to estimate the mass of the black hole. Part 2 is to simulate a ship going around said black hole. Are the fundamental physics properties that we need will be Newton's first and second law and gravity formula. Preview: the black hole has a mass of 1.4 times 10 to the 34th, and this is the simulation, an image of the simulation. Alright, these are our main physics ideas in detail. Newton's first law describes how objects in motion stays in motion unless acted upon by another force, yada yada. And Newton's second law is we need F equals ma so we can derive our position update formula and our velocity update formula. And we also need the one force acting on our system is gravity. So gravity formula, and there's the G constant. So our star's the star's mass is right there. We got the star's position, 1 delta t after the start, and then the black hole at the origin. Our system in this case is the star, and our surrounding is the black hole. All right, so now we got, this is basically all to find Fnet. Then we split Fnet into Fnet parallel and perpendicular. Then we update the star's position, and we draw arrows to show where the star is. And then every time this runs, we take this, is the gravity formula changed up so we can find the position of one of the masses, in this case the black hole, and then every single time we print out what the mass of the black hole is. Then we, after this is all run, we take the average of this number that's get printed out like 400 times, and then we find that that is the average mass of the black hole, which we'll be using in the next part of the lab. So there's that number again, black hole mass. Now we got a ship's mass, we got a planet's mass, we got ship speed, and we got, this is a vector technically, so it's 0, comma, 2 times 10 to the 6, comma, 0. And those are in kilometers too. And that's for part 2, which is another wall of text, I'm sorry. And so we got net force on the planet up here, so black hole to the planet, ship to the planet, and we got Fnet on planet by adding those together. Then we got the same thing again, but for the ship. So then we make our velocity update and position update right here, based on how those things move. Got planet velocity, position, planet position, ship velocity, ship position. That's everything. Again, this is breaking the code in case the ship crashes, and we print out the rest of this, and it shows us this guy right here. Our big blue line is our planet going around, and this is as close as I can get it to the black hole without crashing. I thought it was pretty dang close. Alright. Oh yeah, there's some possibility of error. I think the biggest possibility of error could have been calculating the black hole mass, since it was changing as we were going quite a lot by like almost millions of kilograms, so I think that has their biggest chance of error was calculating the black hole mass. And then so, yeah, although it's a simulation, maybe delta t wasn't small enough. I don't know, I was grasping at the straws there. Alrighty, our discussion and lab questions. So the first question is to discuss how the net force and its parallel and perpendicular components are different from the rate of change of parallel and perpendicular components. Well, the big one is that momentum is just velocity mass, and it doesn't include time. So even though it's rate of change over time, it's still not the force that's exactly acting on one of the things. So, yeah, an Fnet, the parallel component is 0, while the perpendicular is not, because it needs to be changing directions as it's going. So both are based on the object moving, but one is direction, the other is speed, which I guess kind of works. Alright, and so initial velocity of spaceship to orbit around the black hole. I just wanted to get it like as oval shaped as I could without it crashing, and I found out to be 2 to the 10, 2 times 10 to the 6, which was as close as I could get without crashing. Maybe I could have gotten it closer, but whatever. It looks really cool right here. And that is it from me. Thank you very much for watching. I hope you have a good day.